I'm really excited to have Sajjad Nizadi here to host a workshop for us. He's a computer science PhD student at the University of Maryland doing his research in quantum computing, and I've known him for a while. He's a really good guy, and I'm really happy to have him here. And yeah, let's get started.
I'm going to be talking about quantum computing. The official title that I wrote is Quantum Computing for the Gifted Amateur. It's based on a similar title that of a book that I have called Quantum Field Theory for the Gifted Amateur. I kind of like the name, but I think the reason why I picked this name is that I'm going to be assuming no background for quantum computing, but I am going to try and actually delve into some of the computations and some of the actual definitions versus being too high level. And hopefully, you guys can follow along. And if there's any point, there's anything that's not clear or there's a confusion, please let me know. Yeah. So here, there's three examples of current quantum computers that exist. The left one is the one by Google, the Sycamore quantum computer. Middle one is by IBM, and the third one is by Xanadu, which is a startup in Toronto. And I just put them there to show that there's different ways of constructing quantum computers using different physical architectures. The left one and the middle one use these things called superconducting qubits, and the right one uses lasers and photonics. I won't be really discussing the hardware of it. We're just going to be kind of discussing the mathematics of quantum computing and what it's useful for. But just keep in mind in the back of your brain that all the things we're going to be discussing eventually has to be constructed in hardware, and the way that this is done varies depending on the company, and there's a lot of exciting research on that that's going on. So the outline, I'm going to first motivate kind of the area of quantum computing, talk about some of the basics of quantum information, talk about some of the quantum properties which are important for quantum computing and the reasons we really care about this area, give a homework problem of quantum teleportation, discuss some applications of the area, talk about how quantum computing is today, and where you guys can go for more resources if you'd like to get started learning about this after the workshop. So for motivation, I have three bullet points here. Number one, Moore's law is dead. If you don't know, Moore's law says that every 2 years, our computational power essentially doubles. Now, this is a bit exaggerated. Moore's law seems to be slowing down just because of our capabilities of constructing smaller and smaller circuits have started to plateau. And the fundamental reason for that is that at some point our chips are going to become too small so that we won't be able to deal with the errors that are accumulating due to small quantum effects. Quantum effects will occur when you get to very tiny distance scales, which is the scales at which we're starting to approach at the distances that we have to, at the lengths that we have to go to construct these small chips that have a lot of computational power. So one motivation for studying quantum computing is that, hey, if we're already starting to approach a situation where our chips are not working, if we want to make them too small because of these quantum effects, maybe we can, instead of trying to make classical chips, think about how to make quantum chips so that if we're going to deal with these effects anyways, we can use them to our advantage. So classical computing might be slowing down a bit in its progress, and so quantum computing, that's one motivation to study it. A second motivation is quantum advantage. So quantum computers may be able to solve some computational problems exponentially faster than any classical computers can, and we'll talk about this later on in the discussion, where quantum computers allow us to run some algorithms that classically you wouldn't be able to, and so this is a second motivation. And the third one is that trying to build these quantum computers has actually taught us a lot about fundamental physics. It's one of the more difficult technological tasks that we've been trying to attempt to do. And already in the past few decades, the attempt at building these quantum computers has taught us a lot about physics and technology. And once we have powerful quantum computers, we can in fact use these to even simulate experiments and understand more about science, hopefully. These are some motivations for why we care about quantum computing. Any questions so far? Yeah, so let's just dive into the basics of information processing. Let's do a recap of classical information processing. So in classical information processing, we have these entities called bits. That's what all computers use and how computation is done. A bit is something that's going to be in one of two states. It's either 0 or 1. And if you have n bits of information, that means that those n bits can store 2 to the n possible different states, namely all the strings with zeros and ones in each of them. And a classical circuit basically consists of wires and primitive gates which act on these bits. So here is an example of a classical circuit that I've drawn where it takes in n bits of information. It goes through wires and applies some primitive operations like and, or, and not gates. And at the end, you have some m different bits that are an output of this circuit. So a circuit like this would be implementing some Boolean function, some binary function that takes n bits to m bits and does some operation. Is everybody here familiar with the classical circuits and or not gates? So yeah. So this is the model of classical information processing. It's what our computers basically do. At the bare bones, when you're writing an algorithm, this gets translated into some circuit that's implemented on some memory which stores bits. Oops. Now we can further generalize this and look at the probabilistic setting, where instead of having bits that are either 0 and 1, imagine we have a situation where we can store some probabilistic information. That means bits that are with probability 1/2, for example, 0, and with probability 1/2, 1. Imagine just flipping a coin and then covering it before it lands, so that at this point, because of your lack of knowledge, you don't know, was this coin going to be heads or tails, 0 or 1? And with 50-50 chance, you know it's one or the other, so your state of knowledge about the system tells you that the system has to look something like this. This is just a weird way of writing the fact that if I flip a coin, it's either heads with probability 1/2 or tails with the probability 1/2. I could use this intuition to develop a model of computation that uses probabilities, that uses randomness. And then instead of having the primitive objects of computation be bits, which are either 0 or 1, in my computer, they can be random bits, which are going to be some probability of which each bit is going to have some probability of being 0 and some probability of being 1. And so a random bit is going to be written in this form where P0 and P1 are the probabilities that my bit is either 0 or 1. And of course, the sum of these two has to be equal to 1 and they have to be positive so that they are really probabilities. And if I have 2 bits, then I can have some probabilities over all the 4 different ways these bits can be arranged. So the probability that my bits are going to both be 0, the probability that one is 0 and the other is 1, and so on. So in this way, I can think about information probabilistically instead of just classically. Now, adding this extra potential for computation, of course, makes the space of all possible bits very complicated, or random bits, because now instead of having just a 0 or 1 in each register, I can have some probability distribution over these, which it might be very complex. Like I have any numbers for P0 and P1. But this is fine, right? We, in fact, use randomness a lot in computation and, for example, machine learning and different algorithms that today we are fundamental to our computational stack. Randomness is quite useful, and this probabilistic information processing model helps us reason about it. And so similar to the classical setting, in the probabilistic information processing setting, we have circuits, again using and, or, and not primitive gates, as you can see below here, except now the input and the outputs of this circuit are going to not be bits, but these random bits, these probability distributions, as we call them. Now, imagine, for example, instead of having my input to the circuit be like all zeros, like a string of just zeros, I have a string where each of these xi's, x1 to xn, are going to be coin flips. I flipped a coin for each one, and now it's a 50-50 chance of being 0, 1. Then I apply some circuit, and then at the end, I'll have some probability, some y's, which are going to either be 0 or 1 with some probabilities. And then once I've done this computation, I'm going to do what's called measure the distribution or measure the output of the circuit. Measure here just means that I'm going to look at it and then see what the outcome really was. So I had some computation that was done on some coins that I flipped. I didn't know what the outcome of the coin flips were, so it was all random. Then I did this computation. At the end, I don't know what the output is yet, but I can tell you what with what probability which outcome I will see, because I know that what probabilities were at the beginning of the computation. Then I just look at the circuit, and then I'll see some output, right? Like 1, 1, 0, 0, 1 or something like this. And I can tell you with what probability I'll see each one by just doing the computation. Now, this process of looking and seeing which output I actually had is called measuring the distribution. Now, this might seem kind of silly because, hey, why didn't you just at the beginning look at the xi's and see if they were 0 and 1 instead of coin flipping? That's true, because in this model, randomness is really only here because it's a lack of knowledge that we have about the system. But in the quantum setting, randomness is actually something innate. So we need this language to be able to discuss it. This notation is kind of funny, but it's the notation that we're going to use in the next slide. So that's why I began with it. So again, this just means that with probability 0, we'll get 0, and probability 1 will get 1, and that's the state of that register, that bit. Okay? So now we can go to quantum information processing, which uses quantum physics. What is quantum physics? Quantum physics is the physics of subatomic particles, and it has many unintuitive consequences like entanglement and interference, which we will discuss. And in particular, what's important about quantum physics is that randomness and probabilities are inherent to it. It's no longer that randomness is only something that allows us to model our state of knowledge or lack thereof, but in fact, it's something inherent to the system itself. So in the probabilistic model, we said, hey, we flipped a coin, we didn't see that result, so now we have to model it randomly or as a probability. But in quantum physics, in fact, the output of some experiment is really truly going to be random, and so we need to model it correctly in this way. It's not just a reflection of our state of knowledge about the system. So let's again develop quantum information processing the same way we did classical and probabilistic. So a quantum bit, or a qubit, is defined very similarly to the probabilistic or random bits I defined before. Again, two numbers, alpha and beta. Alpha and beta are called amplitudes instead of probabilities now. And we assign these to the basically two possible bits that we originally had, 0 and 1. Now, instead of these being probabilities where we interpret them as saying, hey, with probability alpha, if I looked at this or measured this bit, I would see a 0, and with probability beta, I would see a 1. These amplitudes are no longer going to sum to 1. My only restriction on them is that when you square them and then you sum them, you get 1. So that tells you that the space of all the options for a qubit basically lie on the circle. Any point on the circle defines a different qubit for values of a and b. In fact, it's actually more general than this. A and b can be complex numbers, but we don't need to get into that discussion right now. For now, just assume that they're real numbers. They can be negative, so this is very different than probability theory because you can have negative amplitudes. But what's important is that when you square them and add them, they're equal to 1. And the reason for this is that when we measure it, the way we interpret the probability of seeing an outcome is by squaring their amplitudes. Namely, if I have a bit in the state alpha 0 plus beta 1, if I measure it, like I have some device that measures this bit, imagine the bit is encoding, for example, whether or not some whether or not an electron is moving around a neutron in clockwise or anti-clockwise directions. So clockwise would be 1, anti-clockwise would be 0. So some physical objects that encoding two possible situations, so a bit. Now, in the quantum world, we don't know if it's going clockwise or anti-clockwise. It has some like weird distribution, which is modeled by alpha 0 plus beta 1. Now, if we actually have a device that measures it, we'll get a measurement that tells us, hey, it actually is going clockwise or it's going anti-clockwise. And we can see if the state of the system was alpha 0 plus beta 1, what is the probability that once we measure it, we will see that it's going clockwise or it's 0, the bit. Well, the probability of seeing 1 is going to be equal to just alpha squared, the amplitude squared. And the probability of seeing the bit 0, these are transposed, this should be 0 and 1, will be beta squared. That's why it's important that when you square them and sum them, you get 1, right? So this is, so a quantum, again, to recap, a quantum bit or a qubit is modeled in a similar way to the probabilistic or random one, except we use amplitudes here, which are more general. And when we measure it, we so-called collapse the system into either the 0-bit or the 1-bit situation. And the probability with which this happens has to do with the amplitude squared. Any questions so far?
Oh, we had one question in the
Yeah.
chat over here. One sec. The person just asked, what is the difference between asking Google to pick a random number to a quantum computer picking a random number?
Sure. So the way that I'm not sure how Google would pick a random number, but usually the way that a lot of these random number generators work, what they do is, for example, they either you do something called pseudo-randomness, whereas that they don't actually generate a random number, but they do some complicated computation, and then the output is something that looks random, but it's not really random, right? There's other situations where maybe a random number generator is actually using some quantum phenomena to generate random bits. So if you actually want true randomness, you have to, at the end of the day, access some type of quantum phenomena which generates truly random bits. And now, as I said, I don't know what Google does, if they use some quantum phenomena or if it's some pseudo-random process that looks random, but really there's an algorithm behind it. But yeah. So we saw what a qubit is. So now we can talk about what a quantum circuit is. Okay, a quantum circuit is, again, built out of primitive gates, what we call quantum gates, and now also these things called measurement devices. So as you can see here, a quantum circuit will act on n qubits now instead of bits, which I put here. It'll go through some wires and some gates, like this H gate called the Hadamard gate, the C naught gate, this called the X gate. I'll discuss what these gates are later. And then after having some gates applied to them, at the end there's measurements that are applied to these. So gates, like the classical circuit model, what they do is they apply some primitive operations on these bits, now qubits. And what the measurement at the end does is that whatever the state of the quantum system is, with these like amplitudes, it'll collapse the state into a single string, so a single bits, with probabilities associated to the amplitudes the same way that we saw in the previous section, right? And we'll see an example of a circuit, and we'll by hand try to compute the outcome of small primitive circuits so that we get a feeling for this. But again, very similar to the classical world, except now we have this measurement process at the end to collapse this quantum state into actually a string. What's important is that you always have to collapse it. You can never get any information out of the quantum system without collapsing it first. Whenever you measure your quantum system, for example, your qubit, which was alpha 0 plus beta 1, you'll always either see 0 or 1 with probability alpha squared and beta squared. Meaning that you won't ever be able to learn something about alpha and beta from one measurement. You'll just see a 0 or 1. So this is a very key important fact that some people often when they talk about quantum computing, they say that quantum bits are neither 0 nor 1. They have multiple states in between, and that allows us to encode more information. This is a very false statement because you're not able to actually store that information because if you measure it, it collapses. What it does is that this fuzziness between 0 and 1 allows us to do more interesting gates and more interesting computations that we'll see later on. So this is what a quantum circuit looks like. It's built out of primitive gates, like how in the classical world, you can have a universal set of gates, the and, or, and not gates that can do all computations. You can also have these primitive gates, the Hadamard, poly X, poly Z, the C naught, and the T gate, which does all of quantum computation. And in fact, you don't need all of those 5 in the same way you don't need all 3 for the classical circuits, but it's nice to have access to all 5 to write stuff more succinctly. The Hadamard, the poly X, the poly Z, and the last one, the T gate, these 4, they are applied to only a single bit, like the NOT gate in classical world. And then the C naught, which is that weird symbol looking thing, is the only one that is applied to 2 quantum bits, like and or are in the classical world. These are going to be the primitive gates out of which we can create our quantum circuits. So we can now look at what do each of these gates do. This would actually be a nice thing to write down if you have a pen and paper so that you can remember them and work with them, kind of. The first one is the Hadamard gate, which is very important. What it does, the Hadamard gate, the H gate, if you give it 0 qubit, the qubit which is fully just 0, nothing else, what it outputs is this is called superposition, by the way, when it's kind of fuzzy between 0 and 1. It gives you a superposition with an amplitude of 1 over square root of 2 on 0 and 1 over square root of 2 on 1. So it's equally 0 or 1. To just verify for yourself that this is in fact a qubit, you can see if you square these amplitudes, you get half, and then if you add them, you get 1. So this is a real quantum bit. And if you inputted 1 into this gate, you'd get the same thing, but just a flipped sign on the 1. That's the Hadamard gate. Then we have the poly X gate, which essentially is the NOT gate. If you give it a 0, it gives you a 1. If you give it a 1, it gives you a 0. Very simple. Then the poly Z gate, which is a phase gate. If you give it 0, it does nothing. But if you give it 1, it flips the sign on the 1. It adds a negative to it. So these are 3 gates which are important. We have the T gate, which we won't be using, but is actually very important for the following reason. The T gate, while we're not going to be using here, is actually necessary to have quantum computation that is more powerful than classical computation. You can show that if you had a quantum circuit only made out of these other 4, you can always write a classical circuit that does the same thing basically as fast. But if you had these T gates, that allows you to do more complicated algorithms faster. So this is a very core gate, which is important, but we won't actually be using it for the examples that I have. What it does is it just adds a phase of some complex number. If you haven't seen complex numbers, that's okay. We're not going to use it to the 1. It's like the square root of the Z gate, the 4th root actually. If that doesn't make sense, it's fine. And then we have the only gate that acts on 2 qubits, which is called the C naught gate. What this does is it uses 1 bit as a control bit to flip or not flip the second bit. So if the first bit is 0, it does nothing. If the first bit is a 1, then whatever the second bit is, it flips the value. So it applies a poly X or not on the second one if the first one is a 1. And these 5 are going to be the primitive quantum gates that we can make circuits out of. Any questions so far?
Actually, I do have one question.
Yeah, go for it.
So I might have missed this, so forgive me if I did, but what
No
does the different notation with it being on top and bottom, the like inputs and outputs mean?
Oh, okay, yeah. That's just a notation I wrote for showing you the 2 different possibilities. There's no such thing. It's just 0 coming in gives you that. If 1 came in, gives you that. Is that clear?
Got it. Okay. Yeah, makes sense.
Yeah, it would just be one of them going in. I just put that so you can see the 2 options. Moving on. Oh, that should be a 1 here instead of 0. But put a 1 there. Let's go through this very small circuit and see what this actually is computing, what we expect the outcome of this circuit to be. So we take not a 0 here, it should be a 1. A 1, we apply a Hadamard gate to it, the first gate. Then we pass it through a poly X gate, the 3rd gate, and then we measure the outcome. So let's see what this does. You can follow along if you want by hand, but if you feed a 1 into the Hadamard gate, then we just look over here. What is that going to give us? That's going to give us the following quantum state, right? An amplitude of 1 over square root of 2 on 0 and minus 1 over square root of 2 on 1. So once we pass it through here, when we're over here in the wire, what we have is this funny looking state. Now, once we pass this state into the poly X, what happens is that we get flipped for these bits, right? The 0 is going to become a 1, and the 1 is going to become a 0. What's important is that a quantum state in superposition, that means in this distribution in the middle of 0, 1, when you apply a gate to it, it's as if you're applying a gate to each part of the superposition independently. So it was enough for me to tell you what poly X does to 0 and 1 for you to be able to figure out what it does to this weird state. Because you just look at what poly X does to the 0 part and the 1 part, right? So once we pass the 1 through Hadamard, we get this state. We pass this through the poly X, it flips this 0 to a 1 and the 1 to a 0, and we get the following state here. So now we have a positive over the 1 and the negative is on the 0. Now, this is a state. We have some amplitudes. What happens when we measure it at the end? This is a measurement device. Remember, the probability of seeing a 0 will just be the square of the amplitude in front of it. Well, the amplitude in front of 0 is negative 1 over square root of 2. Negative 1 over square root of 2 squared is just a half. And the amplitude in front of 1 is 1 over square root of 2, which its squared is again also a half. So this state, if you measure it, you'll just get an equal likelihood of seeing a 0 or a 1. Everybody follows? So this circuit here, all it did was create basically a random distribution, uniform distribution between the 0 and the 1 state. It's just coin flipping, essentially. I just wanted to put this like a very small circuit so we can see how you're supposed to think about a quantum circuit and step by step compute what you expect the outcome to be. So now if you actually constructed this quantum circuit on a quantum computer or wrote a program for it, if you ran it, you see 0 or 1. And if you ran it a million times, you would expect that half of those times you'd see a 0 and half of the time you'd see a 1. Make sense? Okay, so now let's recap what we've done so far. We talked about classical information processing and then probabilistic information processing as a prelude to be able to understand the basic components of quantum processing, which is qubits and the way that we're writing them. We talked about quantum circuits and the fact that quantum circuits have these quantum gates and measurement devices. That's how we construct them. We talked about what measurement means and that how when a quantum state collapses, you see an outcome with probability that's associated to the square of the amplitude, the number that we put in front of each of these bits. And we saw that there are 5 primitive gates, which we described, that are useful for us to be able to build quantum circuits out of. Also, one other thing that I forgot to tell you is that unlike the classical world, in the quantum world, all our circuits will begin with n wires and end with n wires. So while in the quantum classical world, you can, for example, have a circuit that begins with 5 wires, 5 inputs, and that has 3 outputs or 7 outputs or whatever. Like either there's duplication that happens or there's an AND that like eats one or something like this. In the quantum world, all circuits begin with like, let's say 5 inputs and and at the end we'll have 5 outputs. There's no either copying of a bit or destruction of a bit that occurs in a quantum circuit. This is actually very key. Just have that in the back of your mind. It's not that important for now, but that is something that quantum circuits have. So now we're going to be talking about 3 of the actually important key properties of quantum mechanics that we'll be able to immediately see just from the stuff that we've learned already. We'll be able to understand what it means that quantum states have interference. If you've ever heard that in like pop science books or something. We'll talk about entanglement and you'll see what entanglement means just using the things that we've learned so far, and also something called the no cloning theorem. These are the 3 things that are useful in developing quantum algorithms and the reason why quantum mechanics is so interesting, and already with the things that we've seen, we can understand them. So we'll begin with interference, and we're going to have some small circuits to compute, and I encourage you guys to compute these circuits along with me with a pen and paper so that you get the intuition of how quantum circuits work. Okay, so quantum interference. Probabilities can only accumulate. You can only add them because they're positive numbers. But amplitudes can actually cancel out. The image that you should have is like two waves that have opposite, directions meeting and then them canceling each other out. And really there is this similar image that occurs with quantum states. We have this quantum interference property. And so for us to be able to see this in action, we're going to compute two separate circuits. It's both going to be a good lesson in like an exercise in just computing basic circuits, and also we'll see how quantum interference actually comes into effect. The first circuit is just going to begin with the zero state, apply a Hadamard gate, measure, apply another Hadamard gate, and then measure. The second state is the same thing, except in the between, we don't look at it. We don't measure it at any point. This will also show us that measurement actually is important, that measuring in between a computation changes the computation, but we'll get to that later. So right now, we're just going to compute these two circuits and see what the outcome of these circuits are. Ready? Let's begin. Let's compute the first circuit. And the way that we usually analyze quantum circuits is that we basically break it up into time steps. And at each of these time steps, 1, 2, 3, 4, we look at what our qubit should be right now at that point, after that time step. So at time step 0, we haven't done anything to the quantum state that's 0 yet, so it's still 0. It's still in the 0 bit, right? Then we apply a Hadamard gate. And then at step 1, we'll just have a Hadamard gate applied to the 0 qubit, which, as we said, the Hadamard gate, it takes the 0 into an equal superposition between 0 and 1. So it's equally 0, equally 1. 1 over square root of 0, 1 over square root of 1. Now what happens is we measure this state. Can somebody tell me what the outcome of this measurement will be? Does anybody have an idea of what the outcome, what step 2 will look like?
Someone in the chat said
Yeah.
1 or 0 with equal probability.
Exactly. Perfect. You'll see, because the amplitudes, if you square them, both of them are a half. The next step, you'll just see 0 or 1, each with equal probability. Great. There you are. So now, at this step, we have to kind of keep the tree of probabilities in mind. With probability 1/2, we have a 0 at step 2, and with probability 1/2, we have a 1. So in step 3, what happens is we apply Hadamard to whatever we have here. Okay? So we apply Hadamard to the 0 with probability 1/2, because we had a 0 with probability 1/2, and we apply Hadamard to the 1 with probability 1/2. So after step 3, with probability 1/2, we'll have this equal superposition between 0 and 1, and this equal but sign reversed superposition with probability 1/2 also. Now, in the next step, again, we do a measurement. And you can do this measurement if, in fact, we were in the 0 case in step 2, then we have this state. If we measure it, again, we'll with probability 1/2 and 1/2, we'll see 0, 1. And here also, you could do the same thing. You'll see we'll have the same occurrence. With probability 1/2, we'll have a 0. Probability 1/2, we'll have a 1. And so in both cases, we get an identical output, in fact. And so at the end of this entire circuit, all we've done is flip the coin. We began with a 0, and throughout this process, the outcome of this circuit is going to be that with probability 1/2, we'll see a 0, and with probability of 1/2, we'll see a 1. So this circuit really just flipped a coin. Coin flipping. Okay, not the most interesting circuit. We could have just stopped at 2, and that would have been the same thing. But there's a point to this exercise. And the point is to see what happens if we didn't make that intermediate measurement between these two Hadamards, and see how interference will actually change the outcome. So everybody is following so far. Now let's compute this circuit. Okay? This circuit without the intermediate measurement between the two Hadamard gates. So again, at step 0, nothing's happened. It's 0. At step 1, we've just applied one Hadamard gate. So we get a 0 and a 1 with equal probability. Now what happens is we have to apply Hadamard to this already Hadamarded state, right? So that means we get a Hadamard on the 0 and a Hadamard on the 1. Now you can expand this out, right? and I encourage you guys to do it by hand while I'm talking. You could expand it, so you get, instead of 0, you get a Hadamard 0, and instead of the 1, you get a Hadamard 1. You write those out, and you'll get something like this. So you Hadamard this state, so you get 1 over square root of 2 times the Hadamard of 0, which is this guy, plus 1 over square root of 2 times the Hadamard of the 1 state, which is this guy. If you write this all out, you multiply these out, you get a half of 0 plus a half of 0 plus a half of 1 minus a half of 1. These two cancel out, and you're just left with a 0. This is what we call interference. That means in the world of probabilities, remember the way we wrote a probabilistic or random bit? Everything was positive. Nothing would cancel out in such a situation. But in quantum bits, because we can have negative amplitudes, in fact, you can have this canceling that happens. So these ones, in fact, are canceling out, and the outcome is just 0. So, recap. Having that intermediate measurement in between them made the outcome of this circuit become a coin flip. 50-50 distribution between 0 and 1. Removing that intermediate measurement allowed this interference to happen, which actually made the outcome of the circuit be the identity circuit, which just takes 0 to 0. That's this was to demonstrate two things. One, what do we mean by interference? We mean exactly this fact right here. That wouldn't happen in probabilistic systems. And this is very core to why quantum algorithms are important. And two, that measurement in between the implementation of circuit destroys the circuit. It actually affects what the circuit is. That means that when we're actually implementing a quantum circuit on a quantum computer, it's extremely important that no measurement, and measurement can be like a light hitting it. It's not like a human looking at it or anything. Anything that interacts with the system can cause a measurement. So it's extremely important when these quantum computers are made that they're insulated as much as possible from the outside world. So no intermediate measurements are accidentally performed that corrupt the computation. Hopefully these two notions of interference and also why it's extremely difficult to actually build quantum computers because we can't have intermediate measurements is hopefully that's been clear. Okay, so now we've done two computations of circuits. We've seen this notion of interference, and I told you that's one of three major properties that quantum systems have in quantum mechanics. The second one is quantum entanglement. Now, entanglement is about how the state of a system on two independent bits acts, right? So let's say I have 2 bits of information. One bit has to do is encoding, for example, whether or not an electron is spinning counterclockwise or clockwise around this, this nucleus, and then I have another electron spinning around another nucleus, again, either counterclockwise or clockwise. Now, again, if I just look at both of these systems, put them beside each other, I have a system of 2 bits. Both are either 0 or 1. So I can describe it as either being a system that's both are going counterclockwise, both are going clockwise. One is going counterclockwise, the other is going clockwise, and vice versa. So there's 4 states the system can have. Now I can write down a quantum state by putting amplitudes associated to any of these 4 states. Now the question is, whenever I have a system made up of 2 different bits, a quantum system, can I have just thought about the system independently as one qubit is over here, I describe it, and then another qubit is here and I describe it? Or no, do I have to talk about both together to be able to see the full picture? And this is what entanglement truly means. So first, let's look at something that is not entangled. That means a quantum system of 2 bits that you could have, in principle, actually looked at each bit individually and described it fully without any problem. So here we have a state on 2 bits, on 2 qubits. So it has 4 possibilities, 0, 0, 0, 1, 1, 0, 1, 1. And all of them will have the amplitude a half. Again, to make sure that this is a quantum state, just see a half squared is 1/4. We have 4 of them. Quarter plus a quarter plus a quarter plus a quarter is 1. Okay, this is in fact a quantum state on 2 qubits, right? Now, can we write this as 2 separate quantum states? Yes, we can. In this way here. If we just think about the first qubit as being an equal superposition between 0 and 1, and the second qubit also being an equal superposition between 0 and 1, if we concatenate these using this operation called the tensor product, this is a mathematical operation that comes up in linear algebra. We don't have to think about it. Just think about it as concatenation. Concatenation, where the bits just go together, and then whatever you have as amplitudes get multiplied together. This is called the tensor product operation. So again, the bits just get concatenated, and then whatever the amplitudes are, they get multiplied. That's the way of putting a system and then like seeing them together. If you just write this out, you'll see that the 0 and the 0, when you put them together, the 1 over square root of 2's get multiplied, and you get a half. The 0 and the 1, when you put it together, again, you get a half, so on and so forth. So I could just write the system of 2 qubits as 2 systems of 1 qubit independently, and then just think about concatenating them. That means that this state was so-called separable. It was describable independently without any loss of information, and therefore unentangled. There was no correlation between these 2 bits that didn't allow us to write it in this way. Okay? Now we'll see an example where this cannot be done, and therefore an example of a state on 2 qubits which exhibits this thing called entanglement. And this is the following state, known as the Podolsky-Rosen state, the EPR state. This is a state with an equal superposition, equal amplitudes on the 0, 0 and the 1, 1. So let's take a second to think about what a system with this qubit structure could look like. That's saying that either, right, for example, if I have 2 electrons rotating around nuclei, either both are simultaneously rotating counterclockwise, or both are rotating clockwise. That means that this is telling me that it's not possible that one is going clockwise and the other is going counterclockwise, and vice versa. This already should kind of show you that, hey, that means that the quantum system, there's some correlation between the 2 parts because they are synchronized with each other. And this can formally be shown. If I have a system that is described in this way, if I try to write it as a tensor product or a concatenation of these 2, I will fail. And I'll show that in a second. But before I do that, this also means that if I have this state, right, think about it this way. If I right now measured this state, the one with equal superposition over 0, 0 and 1, 1, what will the outcome of the measurement be? Can somebody please tell me what the outcome of this measuring the state would be?
The same person answered. They said, They said 0, 0 or 1, 1 with equal probability.
Exactly. So you can see there's a 1/2, a square root of 1/2 amplitude on 0, 0. So when you square that, that's 1/2. So with probability 1/2, you'll see 0, 0. And again, same thing with probability 1/2, you'll see 1, 1. That means, what is that telling you? That's telling you that whatever this state is, if you measure it, the outcome of this system will be synchronized between the 2 bits, right? And in fact, you can go further. You can say that if I just measure one piece, let's say these 2 bits are entangled. This is the way you describe them. This is the state of the system. But they're not local. One bit is on my computer, the other bit is on your computer, right? But we know that the state of both qubits is this following state. If I measured my qubit on my computer without talking to you ever, and I see that it's a 0, I immediately know that yours, when you measure it, will also be a 0 because of the fact that these are synchronized, right? Because if I measure mine with 0, I know that it's the state of the whole system is now 0, 0. It can't be 0, 1 because there's no such thing as 0, 1 here. So my act of measuring my qubit gives me information about what your qubit is. This is why there's this weird spooky action at a distance phenomena that people talk about in quantum mechanics. Very weird, but very easy to write down once we have the mathematical language to talk about quantum bits, qubits. So let's just quickly see why mathematically prove that you actually can't write this EPR state as independent, 2 independent qubits that are just concatenated. Well, if you did just concatenate any two states, let's say they have amplitudes alpha 0, alpha 1, and beta 0, beta 1, then in order for that to be equal to this, we know that alpha 0, beta 0 have to be equal to 1 over square root of 2. Alpha 0, beta 1 has to be equal to 0 because that doesn't exist here. And alpha 1, beta 1 has to be equal to 1 over square root of 2. This means that alpha 0 is both 0 and also cannot be 0, right? Because multiplying it by, or beta 1 has to be both 0 or cannot be 0. By these three equations, you can immediately see that this is not possible. You can't have alpha 0, alpha 1, beta 0, and beta 1, such that when you multiply them out in the way that concatenation works, you get the following state out because of this contradiction. So it's immediately the simple mathematical proof tells us that this state that we wrote here is truly entangled. It's a state on two systems that cannot be independently described on single qubits. And this is a phenomenon that does not occur in the probability world. If you have probabilities, you can write them independently always. And this is what's important. One of the number one, probably the most important thing about quantum entanglement is that when you work with amplitudes, writing amplitudes of a full system often is not decomposable into amplitudes on subsystems because there's correlation between these subsystems, as you can see over here. And it's very important. Any questions about entanglement or anything we've discussed so far?
Yeah, there's one question over
Yep.
here. They say, what happens if you measure one and then perform other gates on the other one? Can we still know exactly the measurement that it will give after, or is the entanglement destroyed?
So that's a great question. Once you measure it, the entanglement is destroyed because now it's the system is 0, 0, but there's no correlation that's going on. But if before you measure, somebody applied a gate on their qubit, right? That would actually, you would be able to now say something about the state of the system after measurement if it's still entangled. But once you entangle it, it collapses the state, and yes. Once you measure it, it collapses the state, and there's no more information that you have about the other person's state. So yeah, after measurement, entanglement gets destroyed. Very good question. Yeah, and there's also a technical detail here. Maybe I should bring up. If this goes over your head, that's okay. But entanglement, even though it's spooky, there's a theorem that you could prove called the no communication theorem, which says that even though entanglement seems like it's allowing me to communicate with somebody else via measurement, you can actually prove that while I can affect the other person's system by measuring my system, if we're far apart from each other and we don't send any information between each other, fundamentally you can't actually use this collapsing process to convey any information, which is important because if you could, that would break Einstein's special relativity, which says that nothing travels faster than the speed of light. Because this happens instantaneously. So you could think, I'm here, somebody's on Mars. If I measure my qubit, and they do, that immediately entanglement occurs. That would be faster than the speed of light if I could use that to somehow convey some information. But while you can't affect their system in very particular ways, the effect is not enough to be able to create any information back and forth, which is significant because that's why there's no contradiction between the existence of entanglement and Einstein's special relativity. That was just an aside, but if anybody has any questions about that, now we saw what quantum entanglement is. This EPR state, in fact, is not only entangled, but you can even measure the amount of entanglement that state has by how off is it if you try to write it independently. Like how wrong would you be? How off would you be if you tried to write it independently? And you can measure how entangled something is by how off you would be. And in fact, this EPR state is the most entangled state on 2 qubits. And it's a really simple state to actually construct using a quantum circuit. And we'll, again, see an example of a quantum circuit, both to see that these entangled states are not difficult things to manufacture, and as another example that you can work with me on of a quantum circuit to get used to this formalism. really, the point of this lecture, aside from giving you some of the basics, is to get you interested in the area and also a little not afraid of the notation, because the notation sometimes gets people gets in front of people so that they can't. It's a barrier that doesn't allow them to learn. So hopefully after this talk, you'll understand the notation vaguely enough so that you can go on to the resources that I give you and learn about the subject more. But here, I claim that this very simple circuit that I've drawn here, if you feed it just 2 zeros, no superposition or whatnot, by the end of this 2 gates, you'll have the Einstein-Podolsky-Rosen state, the EPR state, which is highly entangled. So that means these things are not very difficult things to actually make on a quantum computer. You can make them, in fact, we make EPR states all the time on the quantum computers that we have today. And so let's do the analysis. Again, we break it up into time steps and we look at each time step what our state is. So at the 0th time step, we just have the 0, 0 state because we haven't done anything. At the 1th time step, we apply Hadamard only on the first register, only on the first qubit. So that gives us the Hadamard on 0 state, the equal superposition, concatenated with 0. We could just put the zeros inside these guys when we concatenate them because the amplitude is 1, nothing happens to the amplitudes. And we get this state over here, an equal superposition between 0, 0 and 1, 0. We're almost there, not quite. We just need this 1, 0 to become 1, 1. And the way we do that is we apply a controlled knot. If you remember, a controlled knot, if the first bit is 0, it doesn't do anything. If the first bit is 1, it flips the second bit. So again, we apply a controlled knot to this state. Here, because the first bit is 0, it doesn't do anything. But here, because the first bit is 1, it flips the 0 to a 1. And then we end up with the EPR state as we wanted. So again, starting with just 2 zeros, like just normal classical zeros, applying just 2 very simple quantum gates, you can end up with this maximally entangled EPR state that's very useful. Just to show you that these things are actually very simple to compute. And so we saw already interference, and we saw how that can be used in quantum circuits to delete some things. We saw entanglement and how that's an interesting phenomena, an example of how to generate entanglement using very small circuits. The third important property of quantum information is the no cloning phenomena or no cloning theorem. Quantum information, unlike classical information or bits, cannot generally be copied. So if I right now write 00111 on the ground, you can just look at it and then like beside it write 01100, or I forgot what I said, but you could just copy it. Like there's no issue with copying information. And our entire computational stack relies on the fact that if I have bits, if I have some information, I could just copy it. In the quantum world, this is actually not the case anymore. Often, quantum information, if you try to copy it, you would destroy the original copy. This is not always the case, but in the most general sense, this is the case. Now, this is both positive in some sense and negative. First of all, it's a very different way of thinking about computation when copying is not possible. First of all, you can't measure the system to then copy it, because if you measure, you collapse the first one. And then there's no other like quantum algorithm that you could do to like duplicate it, really. You can in particular cases, but not in general. This is great for security. Why? Because inherently, quantum information is not copyable. It's not stealable. Great. That's amazing for cryptography and security. But on the other hand, it's not great for error correction. So as we'll discuss later on, quantum computers today are very error prone. Because of this phenomena, I told you that you really care that there's no intermediate measurements happening between the circuit, because we saw intermediate measurements can change the outcome of circuit. So it's really important that we insulate quantum information from any error that could cause unwanted measurements occur during the process of a circuit. Now, this can't perfectly be done, this insulation. There'll always be some noise that creeps in and some measurements that happen unwantedly, but that's usually fine as long as we're able to do what's called error correction, deal with the errors. Know that they're going to happen with some small likelihood and be prepared to deal with that. In the classical world, error correction is also used a lot. For example, when I send information, signals, the telecommunication networks, when they send classical information back and forth. Usually because of wind or something, some of those bits are lost in the process. But still, you get, your Wi-Fi, your data is able to give you all the things that you search for without any corruption. The reason is that they use error correction to combat this, so that even if there's some noise, they can still get you all your data. The way that they usually do this in the classical world is that they just copy your data multiple times, so that if one of these bits, for example, gets corrupted, the rest aren't, and then from the rest you can figure out what the original message was. So if I want to send you 0, instead of sending you 0, I send you 0, 0, 0. And then if one of these zeros accidentally becomes a 1, I can just look at the other two and then see that the majority are 0, so I know that the original message was a 0, even though there was some corruption that happened. So cloning kind of is fundamental to the way that we correct errors in the classical world, but cloning is impossible for quantum information, as I just said, by this no cloning theorem. So that means that while for security this is great, for error correction this makes life a lot more difficult, because we can't just copy data, we have to be a lot more smart about the way that we correct errors. And that means there's an entire fruitful, amazing field called quantum error correction, with a lot of interesting things that are discussed there, that tries to combat this. Even though we can't clone information, can we still somehow correct errors? So this is the third property of quantum information that's important, the no cloning phenomena. So this is where the homework comes in. This is what is called the quantum teleportation circuit. I'll tell you why it's called this and why it's an extremely interesting circuit. And now, hopefully, after we've gone through a bunch of circuits together, this circuit, I'll leave it up to you guys. Please take a screenshot of it or something, to step by step, as we did before, compute and see what happens during the process of the circuit evaluation, and see that in fact the claim that I'm about to make is in fact true. I won't wait for you guys to do this. It might take a few minutes to do. I'll just leave it as an exercise for you guys to do later. And I'll tell you first of all why it's called the quantum teleportation circuit, because really it does quantum teleportation. And this is not some fancy science fiction thing. Like, we do this all the time in labs. It's really cool, actually. So the quantum teleportation circuit takes in 3 qubits. The first qubit can be anything, any qubit, and the next 2 qubits are going to be the EPR state, as we saw before. It applies 2 gates, that's it, the C0 in reverse direction, where it is dependent, the control qubit is this one, and then this one is the outcome qubit, the one that is flipped, right? So it's controlling the bottom one and flipping the top one. It applies a Hadamard to the first one, and then it measures these 2. Then, if the measurement is 1, it will apply a poly Z on the third qubit. And if the measurement of the second qubit is a 1, it applies a poly X on the third qubit. And that's it. I claim that if you implemented this very simple circuit on these 3 qubits, the outcome of this circuit, which is going to be down here, is going to be exactly this alpha 0 plus beta 1 with probability 1 is going to be that. Now let's think about what this means. Remember, if you look over here, you see that there's no gate that's implemented between the third wire and any of the first 2 wires. There's no gate that is implemented on both of these. All the gates are either implemented on the first 2 or just the third. And the EPR state is entangled, but that doesn't mean that it has to be somewhere located in one facility. An entangled state can have one piece of it be on Mars and one piece of it be on Earth. That's fine. This is saying that if there's Alice is on, let's say, in her lab, and Bob is in another lab, and from before somehow they had access to one of these entangled EPR states that they shared together. One has one piece of it, the other has another piece of it, and they have it in their separate labs. By me implementing, let's say I'm Bob, this small 4 qubit circuit, 2 gates and 2 measurement circuit on my qubit that I want to teleport and my part of the EPR state, and then doing measurements, and then just telling Alice literally on the phone, like, my first measurement was a 0 or 1, and my second measurement was a 0 or 1. Like classical information that tells her should she put a poly Z or should she put a poly X or not. She'll then go and apply poly X and poly Z on her EPR that she hasn't done anything to up to now. And My claim is that the part of her EPR that she only applied poly Z and poly X to, if I told her to, will end up being exactly the state that I had in my lab. So I've teleported my state from my lab to her lab, which might be miles apart, by just telling her whether or not to apply the poly Z and poly X and using an entangled EPR pair. First of all, that should be really cool if you guys haven't seen that before. This is really teleportation that is going on because I use two classical bits to teleport a quantum bit which has infinite amount of information. The alphas and betas can be anything. The circuit is quite simple, so hopefully you guys can go after the talk and compute it by yourselves, and you'll see that literally this is happening. And in fact, this quantum teleportation, we do it all the time in labs, and it's really cool. Again, this does not violate Einstein's special relativity, because while I am teleporting states, I have to first give a call and say the two classical information, which will take the speed of light into account. So there's no violation of Einstein that's going on here. So this is a really cool circuit, and then hopefully you guys take a screenshot of this, and then just on your own time, actually go step by step through the circuit and see that this is in fact, my claim that I'm making is true. That in fact, if you do the circuit by the end, you'll end up with alpha 0, beta 1 on the third register, which could be in some other lab, which is miles away. Okay, so that's going to be the homework. I still have some slides left, but any questions so far? Now I'm going to talk about one application of the stuff that we've learned, which is quantum money. So money can have, digital money can have two potential problems. One is the verifiability problem, and one is the clonability problem. That means that if I have some digital currency, I want to make sure that my money is not clonable. I can't, on a computer, just make more of it. And I also want to make sure that whatever money I produce as a bank, the digital money, that I can tomorrow verify if in fact I had really produced that piece of cash or not. Now there's different systems out there that do this with some computational assumptions. But in fact, if you had access to quantum states in the way that I'm going to talk about, you can actually get this pretty easily for free. And you make money using this protocol. You first have to pick a random function that takes strings, n-bit strings, to n-bit concatenations of these four states. 0, 1, plus, which is the equal superposition over 0, 1, and minus, which is the equal superposition with the minus on the 1, right? So you have these four states, right? And then for each input s, it will give you like 0, 1, plus, plus, 1, 0, minus, minus, plus, whatever, like a concatenation of these states. It'll give you some quantum state. And the quantum state will be f of s, right? It'll be one of the states with n of these guys concatenated, right? This function is random and it's only known to the bank. Now, this money, because it's a quantum state, this state f of s, immediately by the no cloning theorem, cannot be copied. Great. The money is for free, not copyable. Now, how does a bank verify this cash now? If somebody comes to the bank with a quantum circuit and also a state, the input s to the function that the bank used for making this quantum circuit, the bank would have stored basically what state this should be, like what value 0, 1, plus, minus should be in the state in some database that S is pointing to in their database. And then they just look at that state, and then they construct the reversing process circuit that would take that state to the all zero state. And you can always construct this. So this HB sigma XA is the circuit that if you had, for example, 0, 1, plus and minus in the way that, in a certain way, if you had knew the A's and B's that were used to create that state in the first place, you can just apply the inverse circuit, which always exists in the quantum world. All circuits are reversible, by the way. You can apply the inverse circuit to just take your f of s state now just to the zero state. Now, you can't do this if you don't know what the circuit, what the state actually is supposed to look like to begin with, right? So that means because the bank already has stored that, okay, for this value of S, the state f of S looks like this, and I use values A and B here to construct it, then when I come back to the circuit with my state and the value S, the bank can just go in its database, see like, oh, okay, S was this state, I used A and B, I will use the inverse of that circuit to just apply to the state. If the state is 0, I know that the person was trustworthy. The person actually gave me the state that I gave them. If it's anything else, then I know it was something else because the inverse circuit didn't invert it to 0. So that means simply we have some digital currency which is verifiable information theoretically. That means with no computational assumption, it's unbreakable no matter what. And you immediately have that it's not copyable because of the no cloning theorem of quantum mechanics. Now, is this a practical solution? Not at least today, because we don't have quantum states that I could just give to anybody and whatnot. But it's, I think, an interesting example of an application of the stuff that we've learned so far on how using different properties of quantum information, we could get very interesting cryptographic protocols, for example, that where you can construct money that's easily verifiable by a bank and not copyable at all. Now I'm just going to go through a run through of some quick applications of quantum information. One is to quantum cryptography. Quantum cryptography is a huge field with many different things, but some highlights of quantum cryptography, things that we can do with quantum mechanics, are the BB84 secure key distribution, which is a quantum algorithm which allows two parties who've never met to, over unsecure communication channel, share a private key to then be able to do cryptography with without ever meeting, and by just using entanglement, which is a really cool protocol. There's fully homomorphic encryption, which says that if I have some data and some quantum circuit that I want to implement on this data, but imagine I'm not a quantum computer, I'm just some classical computer, and I want to use IBM or Google's quantum cloud computer to compute my circuit on my data. But I really care. It's sensitive data. It's a sensitive circuit. It's it's my company's own circuit that we worked really hard on, and it's my company's data. And I don't want Google or IBM to actually see this data. Is there a way that I can encode this circuit and this data so that the IBM or Google can still do my computation for me, but they can't actually see anything inside the computation? In fact, there is. This was recently shown a few years ago, actually, but it's called fully homomorphic encryption, and it's a way that you can take your data and your circuit and encrypt them into like larger data and circuits, so that the computer actually can't, by looking at these encryptions, figure out what the underlying circuit or the underlying data is, but still can use their computational power to implement this encrypted circuit on the encrypted data and then send it to me. And then when I decrypt it, it's as if I just run the circuit on my data to begin with. It's a really phenomenal application that exists. So this cartoon image here shows it. Like I have some data, I encrypt it, I send it to IBM. IBM just applies a circuit on the encrypted data and then sends it back to me, and I decrypt that and I get the circuit on my original data. So it like commutes the circuit and the encryption. It's actually a really cool application. Another thing is verifiable quantum computing. So if I have a classical computer and then I want to use Google's quantum cloud, is there a way that I can guarantee that they're actually running the circuit I told them? They're actually doing the quantum thing that I told them, and they're not just telling me, yeah, for sure, the outcome was 1. And there is, in fact, there's something called a verifiable quantum computing protocol that came out a few years ago that shows that I can just, by communicating with Google or IBM's cloud, verify for sure that the circuit that I told them to run was indeed the thing that they ran. And you can see the cartoon image. I have some quantum circuit I want to run. I'm not a quantum computer myself. I send it to them. We do some rounds of communication, and the outcome I'm guaranteed was exactly the outcome of the circuit that Google ran. These are all really interesting protocols. They're very difficult to describe. But there is an interesting area. So that's some applications, some like highlights of quantum cryptography. And on the algorithm side, some highlights of quantum algorithms, there's something called the Shor's factoring algorithm, which says that if I give it a big integer n, it is able to find for me really efficiently the prime factors of n. Why is this important? Because classically, on a classical computer, this is believed to be extremely difficult, exponentially difficult to do. If I give you a number, tell me its prime factors. So I tell you 21, you tell me 3 and 7, right? But for huge numbers. This is believed to be extremely hard classically, and in fact, this belief led us to use this as a fundamental building block of the majority of encryption and security protocols that we use over the internet today, so-called RSA encryption. So in fact, having a large enough quantum computer will allow us to run the Shor's algorithm and break the majority of security protocols that exist today on the internet. Thankfully, there's something called post-quantum cryptography that's starting to be worked on, which is coming up with ways of building secure systems which are resistant against quantum computers. But as it stands today, the majority of internet security protocols are not resistant to Shor's algorithm. And if we get a big enough quantum computer, maybe in the next decade or two, all of these can be broken. So there's a lot of effort on governments and companies trying to move away from RSA to post-quantum cryptography, so that this won't happen in the future when we have bigger quantum computers. Again, Shor's algorithm, it takes an integer, finds the prime factors fast, which is believed to be hard and is the foundation of much of the security that we have on the internet today. So that's an application, a cool application, a bit of a pessimistic application, nonetheless. Another one is quantum machine learning, where there's still a lot of debate as to how important quantum machine learning really is going to be, because there's still not that much theoretical effort that's been on it. But in a future where we would have very noisy quantum computers but that are still powerful, potentially quantum machine learning might be more useful, because while these algorithms like Shor's algorithm, they need very precise things going on in the circuits. In machine learning, a little bit of noise, in fact, is usually fine. So quantum machine learning is another future directions in quantum algorithm that people are working on. And the third, and probably most important, is quantum simulation, which is the original reason why Richard Feynman said that we should build quantum computers back in 1982, which allows us to simulate quantum equations efficiently, which we can't do right now on normal computers. And this will be useful because it'll allow us to do computations for quantum chemistry, to discover new materials for manufacturing, and to compute information about pharmaceuticals, which will allow us to find new drugs, and so on and so forth. So really, there's a plethora of applications, from security to ML to the most important, which is quantum simulation, that are coming out of this effort to work on quantum algorithms. Okay, we saw quantum. Just a run through of some applications. Now the question is, where are quantum computers today? Do we have quantum computers? First of all, yes, we do. We have a lot of quantum computers. IBM, Amazon, Xanadu, PsiQuantum, IonQ, Microsoft. All of these have quantum computers now. But the quantum computers are small. They only have about maybe 50 to 100 to 150 qubits. Compare that to your computer, who has gigabytes and gigabytes of storage space and processing units. It's just 150 bits essentially that they have. So they're very small and they're extremely noisy. So it's hard to actually do stuff with them. Even with those restrictions, we have kind of drifted into the era called NISQ, the noisy intermediate scale quantum era, where while the majority of things we want to do with quantum computers are still not possible because A, our computers aren't big enough yet, and B, they're too noisy, it's starting to be possible to do some applications on them in the near future that might be useful. And hopefully 5 years ago, we weren't even close to here. So the hope is that in the next decade or two, we'll basically be ramping up in technology and we'll reach a point where we can actually implement these more sophisticated algorithms like Shor's algorithm or quantum simulation and so on our computers. To do that, we have to, one, be able to scale up our systems, and B, reduce the amount of noise using these error correction protocols I discussed before. But even though it's still a decade or two left until we get the more real applications out of this field, there's this NISQ era still has a lot of potential. In fact, very recently, you might have seen headlines saying that Google or other companies have achieved what is called quantum supremacy. Quantum supremacy means that they were able to use their in-house quantum computers to perform some computational task that is extremely hard, basically impossible to simulate on the best supercomputers in the world. Now, that computational task, unfortunately, is not a useful computational task, but it's just a proof of concept showing that we are able to do something, at least on these quantum computers right now, that already is not accessible to the classical supercomputers of the world. Now, if we can develop these further, maybe we can do some useful things that are equally not accessible by the classical computers of the world. So we'll see how it goes. It's an extremely exciting time for quantum computing today. A decade ago, we were just basically theorists working on this, but today there's a lot of companies working on it, a lot of money put in it, and hopefully there's a lot of advances that we made in the past decade. And then the hope is in the next few decades, this will really become a core part of the computational stack. And I really do encourage any of you who are interested to learn more about the subject. It's a very mathy subject. It's a very physicsy subject. If you do want to go into this area, you will have to study some subject like computer science or math. But I think is a very worthwhile subject, and it's an exciting area to be working in. And I think now's the time to get in it because it's really ramping up. And that's it for my talk. And here are a bunch of resources that I think are important to get started with, some basic ones. Qiskit, IBM has a programming language called Qiskit where you can write quantum algorithms with, like the circuits that we made together. You can code them up and see the results for yourself. I highly encourage you to go and learn the programming language Qiskit and start working with it, playing around with it. IBM has a textbook called Qiskit Textbook Online where you can use to, one, learn more about quantum computing and also learn about their programming language and start building simple programs. The majority of the programs that you'll write, you'll just run them on your computer because they're small, they can be simulated classically. But if you want to do more larger stuff, you can in fact get credits to run your circuits on IBM's cloud quantum computer, which is really cool. So the Qiskit programming language and textbook, highly recommend it. There are YouTube videos, a playlist called Coding with Qiskit by IBM, which are nice too. On the more mathematical end and more core end, there are a lecture series of a course by a professor called Ryan O'Donnell at Carnegie Mellon University, which I highly recommend watching if you want to really delve deep into it. It won't be easy, but I think it will be fun and worthwhile. And there's also a classical book by Nielsen and Trong called Quantum Computing and Quantum Information. It's a pretty big book. I don't recommend just jumping in, but if you want to have a textbook to follow, like the core theory, that would be the one to go to. But again, I think as people beginning to learn about this area, I would recommend reading the Qiskit textbook, learning the programming language, begin watching some of these like videos by either Coding with Qiskit or Ryan O'Donnell's lectures. And then if you guys are going to a college or university or something, this is a mathy area, so take some math, take some linear algebra, maybe minor in math or something, and that would be the best way to go forward if you're interested in the area. Hopefully, I didn't bore you guys too much, and I'll just take any questions right now.
Hi. So
Hi.
you just said that like if we like I'm at university, so if I want to take courses related to this, it would be mostly math courses. But should I also take physics courses, or is that not really required?
I wouldn't say to you not to take physics courses if you want to, but I'll put it this way. I work in quantum computing and I've never taken a physics class. My background is in math and computer science. And while there are advantages to having taken physics class, I think it's much more important to know math and CS. In particular, it's important to know linear algebra, be very good at linear algebra. So if you have linear algebra classes in your university, I recommend taking those. And also a class on algorithms or complexity theory would be nice too. And then, of course, I think you could just jump in to learn the area.
Okay.
You don't really need a physics background for it, but it wouldn't hurt.
Okay, thank you.
Welcome.
We also have another question over here in the chat.
Go for it.
So they're saying how is all this going to be possible if we can't store quantum states for very long? Like in classical computers, storage like RAM is essential. And then he's asking if like this is possible, like maybe like quantum hybrid computers that partially run on quantum circuits and classical digital computers. Would that be
Yeah.
possible?
So that's an important point. Quantum decoherence is a big issue right now. So aside from the noise that comes from outside, quantum states only you can really hold them for a couple like seconds or so. which means that you can't really store quantum information. Maybe in the future that will be solved and that we can store quantum information, but I think the majority of direction that people are going right now is the hybrid direction. So quantum circuits are going to be a use case only. They're not going to replace classical computers, I don't think, ever. They're going to be like the way that your computer has a GPU or like a CPU that do different functions. You'll have a QPU, maybe not on your computer, maybe in a like cloud computers or something, that are used for particular tasks which are difficult for classical computers, but it won't replace the entire stack. It'll be part of the computational stack in the future. I think that's where people are thinking about it. So your information will be still probably stored classical in the next few decades unless we make some major discoveries. But then you'll be using these quantum, cloud services or whatever in the future, hopefully that they're developed further to do particular computations that will be difficult to do classically, and then you mix that with in a hybrid way with the classical computing stack to do more stuff. Yeah, a great question.
I also have a question actually.
Okay.
This is more, I guess. I know you mentioned that the hardware differs a lot between a couple of the different quantum computers you mentioned, but I was just curious, do you have any resources where we could learn more about maybe how one of those works? Just because I'm kind of curious, like how we would actually physically like run one of these circuits.
Right, nice. Also, to the first question, my answer was very geared towards quantum algorithms and quantum cryptography and that type of stuff. If you do actually want to like physically build quantum computers, like as an engineer, not as like a computer scientist, there you do need physics because you need to actually know about the physics of the system. Not too much, but yeah. So to your question, a resource to learn about how one of these computers is made. Let me think about that for a second. So there's, let me just say a thing, and then maybe right now I don't have a resource on top of my mind, but I can forward something to Hamid later. But I can talk about this, that there are multiple different architecture, basically. So in the classical world, and maybe in the like 50s and 60s, there was multiple ways that we thought about making computers. We had like vacuum tubes, we had mechanical computers, we had like all these different light bulb systems. Until basically in the 60s or was it 70s, the transistor was discovered, and the transistor was so much better than all of these other systems that basically we forgot about everything else. Every computer is just made out of transistors, which allow us to encode information and compute, right? We haven't had the transistor of the quantum world, so there's actually a lot of different ways of encoding quantum information that are basically it's not obvious which system is better than the other. And that's why different companies are betting on different things and their different expertise to develop quantum computers out of different tools. In order to have a quantum computer, you need a couple things. You need some type of quantum system. That means a system that can be put in these like superpositions that to encode quantum information, qubits. You need to be able to apply these quantum gates to them somehow, and you need to be able to apply measurements. So there's one primitive, one way of architecture is the photonic way, where they use light to encode quantum information. So the qubit, the data of the qubit is actually going to be essentially the polarization of light, if you've ever heard of this. So the 0 and the 1 are going to be whether or not it's horizontally or vertically polarized, the light. Light will most likely be lasers here. And then the entanglement comes from the state of the system where it's somewhat, it's like a amplitude mixture of being horizontal or vertically polarized light. And then the way you apply gates is by passing these lasers through like interferometers and like basically optical gadgets. And measurement is just going to be devices where basically the laser hits them, and then you see whether or not it is or is not horizontally or vertically polarized. So that's one method where like the companies Xanadu in Toronto and PsiQuantum in California are trying to develop computers out of. There's some advantages to it, namely that actually is very noise resistant. These lasers are very noise resistant, so you can make quantum states that basically don't get destroyed. The only issue is that because they're very noise resistant, it also means it's extremely hard to implement gates on them. So there's a give and take there. On the other hand, there's companies that are doing but quantum computers based on these things called ion traps, which I have no idea what that is, but like IonQ does this stuff. So maybe you could search the company name IonQ and you'll see what ion traps are. Google and Amazon and IBM use superconducting qubits to systems to construct their qubits, which is a whole other area. And let me see, are there other, and there's other ones too, like Microsoft does this very interesting thing called topological quantum computing, which is extremely difficult to describe, but these I think are the four main ones. Trapped ions, photonic, superconducting, and topological. So if you want to like search up these four names, topological quantum computing is probably the most difficult to understand, but photonic quantum computing, ion trap quantum computing, and superconducting quantum computing. And if you like go on the websites, like I think Xanadu for the photonic stuff has like some articles about the basics of how they develop their stack. FYI, it won't be simple to understand because this is very extremely technical physicsy engineering feats to develop. It won't be as simple to understand, but I think it's still nice to go read about these. So yeah, I recommend searching these four names, essentially the four different types, and then these companies are developing them. They usually have some articles about them, trying to explain it in basic terms.
Yeah, thanks a lot. That was helpful.
Welcome.
I also had a question.
Go for it.
This is more related to like AI and machine learning stuff. So like in the future, like when we're trying to like develop more advanced and like powerful machine learning algorithms and like AI systems, like do you think that quantum computing would be necessary? Like would they have to move to like quantum computing to be able to like compute these types of systems? Because like you said, like Moore's law won't really be applied anymore since
Yeah.
so like what do you think about that?
You know, the honest answer to that is that, like, as a scientific community, we honestly don't know. We don't have a good answer to that yet. We're still trying to think about quantum machine learning and quantum algorithms, how they can help machine learning. I think there was some progress made on like thinking about these problems, but I think the honest answer is we genuinely don't know. This is a big open question, and you know, maybe some of you will come work on the field and figure out either way. But yeah, it would be great if that's the case, but we're not sure if right now quantum computing would be able to give us that advantage in those particular problems that we need solved to be able to help machine learning in the future. So we don't know.
Okay, thank you.
And yeah, as an aside, I showed you a lot of advantages to quantum computing, a lot of algorithms that you can solve, but there's a ton of algorithms, a ton of problems that are also hard for quantum computing. Quantum computing, often people in popular media kind of say like quantum computing, because it can be in all these different states, can just do all of them and then figure out, no, it's none of this business. We saw like it's actually really hard to come up with good quantum circuits. And it's particular problems like quantum simulation, like Shor's algorithm, like some of the stuff that we saw, that we found good quantum algorithms that there's no classical versions for. But that doesn't mean that quantum computing is like this tool that we can just hit at any problem and it will give us advantage over classical computer. Most problems, it won't do any better than a classical computer can. It's those particular problems where it can, which is very exciting. And that's worth investigating and really worth pursuing the subject because those problems are significant problems. But it's not a catch-all. Definitely won't solve like NP complete problems if you know what those are, like traveling salesmen and stuff. But yeah.
Okay, thank you. And there's another question. Do you believe that quantum computing will be available to the public? And
I mean, it is right now. You like IBM and Google's quantum computers, and I think Xanadu's too. They're, I mean, they're small quantum computers. They have what, like 50 qubits or something. So you can you can't really do anything useful with them. But they're open to the public. You can go and register and get time to use them, and then you can write for example, a Qiskit program, and then schedule a time on their cloud to actually run your Qiskit like quantum algorithm, quantum circuit on their actual quantum computer, and you can do that today, like for free. So it's already available. But if you mean, do you think in the near future we'll have quantum computers that can solve all these difficult problems that we can't do classically that will be available. I think most people think in the next few decades, but not soon. Yeah, I do actually recommend like go learn the Qiskit language, write some basic like quantum circuits yourselves, and then like schedule some time to run it on their quantum computer. That's pretty fun, I think.
Okay, thank you.
I have
Go for
another
it.
quick question. Do you know if there are any professors that work in the field of quantum computing at McGill University?
In McGill, I don't know, but University of Montreal, there's a bunch. Sherbrooke also, there's a lot of quantum people.
Okay,
You
thank
search
you.
Sherbrooke quantum. There's a lot of people I know in the University of Sherbrooke, and then University of Montreal. I think there's a couple people there, but like Nicolas Castea, I think is there, and some other people. But yeah. But I don't know about McGill. I don't think there's anyone at McGill. I might be incorrect though.
Okay, thanks.
Welcome.
I don't think there are any more questions. There's nothing in the chat and no one's unmuting.
good.
So I think that's it for this workshop. Sorry, I don't have my camera on. It's my Wi-Fi. I don't know, it won't allow me to turn that on. But
No problem.
thank you so much for this workshop. And also, if any of you guys are interested, we also have a mobile development workshop 2 weeks from now, which you guys can attend. And also, there's Learnathon 22 in the summer, where we'll be hosting, a bunch of workshops on AI, web development, cryptography, and a bunch more things, which you guys can also attend for free. And yeah, thank you so much for hosting this workshop on quantum computing. I'm sure everyone really enjoyed it. And yeah,
Yeah, it was a pleasure. I hope some of you took something from this talk. Okay.
yeah,
See you guys.
thank you so much. Have a good day.
Bye-bye.
Bye, guys.